Hi, I'm Tommaso, PhD student at Graz University of Technology.
And I'm Daniel, also a PhD student at the Graz University of Technology.
Welcome to Bridge the Gap, the physics-oriented podcast,
in which we give insights into various research topics and the life of scientists.
And by the way, if you want to contact us, you can drop a line to our email address bridgethegap@tugraz.at. Hey Daniel.
Hey Tommaso.
In today's episode, we're going to talk about the relation between physics and philosophy.
That sounds very intriguing.
It is indeed. And you know what?
What?
I couldn't come up with a single joke.
This saddens me deeply because you really know how much I love your jokes.
Well, you know what? For a split second, I almost believed you. But in any case, as I said, today's episode will be pretty special in a sense that we will have two guests, Axel Maas, Professor of Physics from University of Graz, and Berghofer, postdoc in philosophy at the University of Graz.
As always, we ask some of our listeners what they know about the philosophical implications of quantum mechanics, and here are some of their answers.
I don't know what is a collapse of a wave function. I would say that philosophy can definitely help to give a more standardized definition on what exactly it is.
Well, when a measurement is conducted, the particle or whatever it is picks one state, so the probability distribution goes away, density goes away, and that's what they call the collapse of the wave function, I think. And well, the philosophy makes claims about how this might be interpreted.
Today's a special episode. We have two guests, Berghofer and Axel Maas from University of Graz, and we will talk about physics and philosophy. So would you guys please introduce yourselves? Philip, let's start with you.
Okay, thank you so much for having us. So I'm Philip. I'm a postdoc at the philosophy department at the University of Graz. I'm working mainly on epistemology, phenomenology, and philosophy of physics. And this is the reason why I'm here, right? Because today we are supposed to talk about philosophy of physics. And yeah, I'm very happy to be here.
Okay, my name is Axel Maas. I'm a professor at the physics department, and I'm doing basically all kinds of fundamental physics, starting from strong interaction physics, neutron stars, up to things they do at CERN, like Higgs physics and quantum gravity. And as such, start to wonder about what all of that means, and that is how I got into contact with philosophy people.
Yeah, it's probably worth mentioning that you two hold a seminar lecture together.
Yes. So this is now the seventh time that we are co-teaching a seminar on philosophy of physics. In this term, we do it on symmetries, but the last time we did it on quantum mechanics or philosophical interpretations of quantum mechanics. So yeah, we're very much looking forward to talking with you.
But as well, we also have published a book on the symmetries in philosophy and physics questions. Yes,
we have co-authored the Cambridge Element on symmetries and gauge-event approaches to particle physics.
Nice. Can't wait to read it.
Yeah. Okay, so then let's start. And could you tell us what is the connection of physics and philosophy? Like, why is it important to have philosophy in physics?
Yeah. So prima facie, they're very different disciplines, right? And when I started studying both philosophy and physics. And for me, this was not connected very much, right? I wanted to understand how does the world work and what does it mean to know something, right? And then I think only very late after I finished my bachelor in physics, I realized that there is something like philosophy of physics. And I think very briefly speaking, I think the main motivation for philosophy of physics, or the main idea behind philosophy of physics, is that we do not just want to calculate with our theories and to make predictions with our theories, but to really understand what the terms stand for, to really understand what the theory tells you about the world. And one very nice example, and I guess we'll be talking about this, is, for instance, quantum mechanics, right? So quantum mechanics is super successful, the predictions are super successful, but there are terms like the wave function where it's not immediately clear what does it mean, what does it represent. Is it something that is physically real? Does it exist out there? Or is it just a mathematical tool? And basically, very basically speaking, in philosophy of physics, you interpret physical theories. And quantum mechanics is a prime example, but this is also true for other physical theories, also classical mechanics. There are also some philosophical problems in classical mechanics in the sense that it's not immediately clear what are the implications of the theory. And also, one further aspect to all of this is that typically you don't have a unique theory, right? A unique mathematical formalism that describes reality, but you could always reformulate it in certain ways. And then again, it's not clear how do the different formulations correspond to reality.
So this is in a way how philosophy can help physics in
Exactly. So this is the one direction, right?
Okay.
How it makes sense to think about theories. And then of course there's also the other direction, that if you're a philosopher and if you do metaphysics, if you think about, for instance, what is the nature of reality, what is the nature of matter, what is the nature of time and space, then of course, I don't know, 500 years ago, 600 years ago, 1,000 years ago, it made sense to think about this a priori, right? But now, in face of all the successful scientific theories that we have, it would be quite naive to think you can discover the nature of matter, the nature of time, by just thinking about it and not taking a look at the, currently at least, most successful scientific theories. So it goes both ways.
Well, I have a question for you, Axel, at this point. So given that this is the philosophical interpretation, let's say, what do you think is the role of physics in understanding reality? Meaning, like, I'll also tell you a bit more what I mean. Is it a coincidence that we can use physics or physical theories to describe reality? Or is there something deeper to it?
There are two layers to this question. The first is, do we share a common reality? If we do, then we can, of course, start to model it something and discuss about it and try to find common ground. That is the basic assumption that you have when you do physics, that this is possible, that you have an observer-independent reality. And the second layer is, can we do this how we do it today in terms of mathematical theories? That is far less obvious. And there are very powerful writings about that this is basically coincidental. There are questions whether math is out there and we are just using it, or math is created to be using it. So from that point of view, how we do it is, it works. I mean, the basic point is physics is defined as an empirical science. We figure out empirically math works to write down theories. So we assume that this is relevant and that is possible, and we use it.
Yeah, so absolutely. There is this very nice and famous article by the physicist Eugene Wigner that's called something like the unreasonable effectiveness of mathematics in natural science. And this is precisely this question, right? Why is it that mathematics can be applied so successfully to our world? It's often called the application problem or applicability problem. And like Axel said, it's not a priori, it's not prima facie clear or obvious that this will work, right? That you can use mathematics to describe nature, describe reality. We are very much used to it now because of, all the
1,000 years of success.
At least since Galileo and Newton. But before this, it was not obvious, and it's an open question, it's an open problem. Like Axel said, it also relates then to questions about the nature of mathematics, right? Is mathematics an invention by humans, or is it the discovery of humans? So there are very many interesting layers to this question.
So currently, all the physical models we have, there are or some of them are very successful, right? Like particle physics, for example, right? But and general relativity, but they're not perfect, right? So all the current models we have of physics are not correct in some sense, right? There must be some fundamental flaw, right? So will we ever be able to find a model that really completely describes physics?
Good question. We have discussed it in many occasions, also in lectures. So first of all, we have basically right now two theories. That's general relativity and particle physics. And that basically describes everything we know. Then there are two reasons why we know that this is not the end. The one is we just have observations which cannot be described in this way, especially astrophysical observations. And the other thing is they have mathematical features which tell us we are limited. So we know that these are not perfect descriptions of nature. They have singularities which don't make sense. So they tell you there is an end. And that is not something surprising. Things like the same signatures appeared to all levels of theories we had in the past. Okay. Will we ever have one unique theory? So combining general relativity and particle physics requires to quantize gravity, at least to the best of our current knowledge. And let's say within the last 25 years, huge step forwards have been made. And there are quite a few people who start to make regular calculations which involve both aspects of that, which also includes my own research. Also papers about Higgs physics and quantum gravity. So it is not that we are far away from getting these two together. Still, what emerges from that doesn't explain everything and still has mathematical singularities, which indicates that there's not the end to it, at least as far as you understand right now. Now, there is multiple possibilities things could proceed. We had this as various pictures. First, we will discover another theory ad infinitum. We'll find one final theory which necessarily needs to explain its own existence. which is something which we don't have even the slightest idea how to mathematically formulate a theory which can predict, which is axiom-free and therefore predict its own existence. Or which I find always very odd is the idea that you have a circular theory, so that at some point a theory refers to a previous theory as its reason. And that's just the possibilities people have logically thought of.
Yeah. So for physicists, I guess the main intuition is always to unify, right? So physics to some degree or to some extent has been very successful. It's been very successful history of unification. I mean, very, very roughly, right? At some point in antique Greece, people thought there are different physical theories or that the world works differently here on Earth than compared to the stars, right? And then we had something like gravitation, right? And we see, okay, when the apple falls down on Earth, it's the same mechanism that holds the planets together and stuff like this. That makes the planets go around the sun. Then, of course, we have electric forces and magnetic forces that have been unified and so on. So I guess for many physicists, the hope is to have this kind of theory of everything, kind of unification of all the forces that matter, that describe reality. But of course, again, this is not settled, right? It's not clear and it's not obvious that this will happen. And it's a bit funny because I think 2 terms ago we had a course on time, right? So what does physics tell you about the nature of time? And again, it sounds very reasonable, right? You say, okay, you want to know how works time or space, so you look at the best physical theories. But then you do it, for instance, for general relativity, and then, yes, you explain, but still, we know that general relativity is not the end of the story, and we have like very, very different versions of quantum gravity at the moment. And then it gets a bit frustrating, right? Because so when you think about, hey, what can philosophy contribute? One of the reasons why there's not a final answer, right, at the moment to questions like what is time and space, it's not like that it's philosophically problematic, but part of it at least is that we don't have at the moment like a final physical theory. So we don't know exactly. Research in physics will go in the next few years.
Mm. And do you think if we should find this theory, that it would be unique? Or do you think it's possible that there are several theories that give exactly the same observable predictions? Because then what would you decide for to be reality?
Yeah.
Indeed, every theory which we have at the moment has this feature, that you can rephrase it in different ways with different relevant entities. These are mathematical exact reformulations. So it's not like they are different theories. They're mathematically uniquely related, but they put different objects and different relations as the central objects from which the other derive. So we have already the problem. And basically we had the problem since classical mechanics, because in classical mechanics, you can either do like Newton, hey, I have a particle and the particle moves because of forces, or you can take Hamilton's principle. There's a selection criterion among all possible paths, and that tells us which is the path, and the particle is nothing more than a marker on the path. So the path becomes the basic entity.
Yeah. So in philosophy of science, this is called the underdetermination problem, in the sense that you have different, or at least you can have different physical theories or different scientific theories that are empirically underdetermined, in the sense that, the same empirical evidence supports both theories to the same extent. And then there is cases in which it's like in principle impossible to have an experiment that would decide between the theories. So what Axel was describing, really cases where you have different formulations of the same theory, different mathematical formulations that are mathematically equivalent. But it can also happen that you have very different theories, but they are empirically equivalent in the sense that there is no experiment that can decide between them. And then, this is again a philosophical problem, right? So how do we then distinguish, or how do we prefer one theory over another if there is no empirical criterion that we can use? Something that is often discussed and used is, of course, Occam's razor, right? You try, or you think, okay, one theory might be simpler than the other. One theory might postulate less amount of entities than the other, so you prefer the simpler theory. But it is also not always possible to say what does it mean that a theory is simpler than another. And here, for instance, the many worlds interpretation of quantum mechanics is a nice example, because on the one hand it's super crazy and you have infinitely many entities, so it is very much not moderate and very much not modest when it comes to the amount of entities. But when it comes to the formalism, it is simpler than other interpretations of quantum mechanics. It's simpler than Bohmian mechanics, where you have more equations than in the many worlds interpretation.
On top of that comes a resource problem. We have only a finite number of experiments, we have a finite number of measurements. And so in most cases, you can prove that there is an infinite number of possibilities how to mathematically describe a finite number of experiments. So again, that makes a hard problem. It's just a practicality problem. It's not something which is not solvable in principle. You just need to do an infinite number of experiments, but it's of course unsurmountable in practice.
Before moving to the specific part of the measurement problem in quantum mechanics, I would have a question which is related to the free will. So if we, for example, it is said that if you have the laws of physics which are deterministic and you have given your initial condition, then in principle you can evolve whatever system, the universe, in this limit, and then you have, a deterministic evolution. So how does this relate to the existence of the free will, for example?
So this free will debate is very old, right? So before the rise of physics or the success of physics, before the rise of Newtonian mechanics, it was God, right, who played this role in the sense that people were wondering, right, if everything is predetermined by God, if God knows everything that will happen, how can we have free will, right? If it is settled from the beginning of the universe that I will raise my arm now or raise this cup, how can this be a free action? So God has been replaced in these discussions right now. It's the laws of physics, in particular because classical mechanics and Newtonian mechanics is a deterministic theory. And basically in philosophy, you have two options, there are two logical options, right, that are called compatibilism or non-compatibilism or incompatibilism. Compatibilism says that free will and determinism are compatible. It is possible that world or reality is described by deterministic equations and still you have free will. And incompatibilism is the view that this is incompatible, right? If the world is determined, then you cannot have free will. I think most physicists are incompatibilists. Most physicists think that if reality is determined, then there is no place for free will. But some philosophers think that this is compatible, that it does not matter so much that it is pre-settled that you will do this, but that what matters more are the reasons for which you do this, the causal history of your actions. If you do this because you thought about it and you are convinced by this, and then it is, so to speak, yes, your free will to act like this, then it is more free at least than when you're in some sense forced by it or misinformed or whatever. But this is an open problem, of course. And if you're an incompatibilist, if you think that determinism is incompatible with free will, then of course physics matters very much, right? Because then the question is it true that reality is determined? And classical mechanics would say yes. Quantum mechanics, at least in its standard interpretation, would say no, reality is not determined. And then there would be more place for free will. I mean, this is a super complicated debate because some people then say yes, but the brain is governed by laws that are not so much governed by quantum mechanics. So the brain is more of a classical mechanism. So even if quantum mechanics is indeterministic, maybe the stuff that plays a role when it comes to how the brain works, maybe this is still determined in some sense. So the questions are very complicated, but at least prima facie there is this huge impact on this question, yes.
So you briefly brought up this topic before of this many worlds interpretation, right? So like the measurement problem. Could you explain what it is and maybe give an illustrative example for it is?
Okay. If we to oversimplify things, the measurement problem I think has two dimensions. Often it is phrased like this: why do we not observe microscopic superpositions? And maybe more specifically, when you think about textbook quantum mechanics or Copenhagen quantum mechanics, why is measurement so central for quantum mechanics, right? What does it even mean to say that the measurement is performed? Why is quantum mechanics a theory in which an operational notion like measurement is so central compared to any other theory that we had before, right? Compared to classical mechanics in particular? And to make it a bit more formal, so typically it is said, right, in quantum mechanics that the state of the system is completely described by the wave function, and then it is said that the wave function behaves or evolves according to the Schrödinger equation. And then John Stuart Bell, famous physicist, said, this cannot be the end of the story, right? Either the wave function is not everything or the Schrödinger equation is not true. And this is for the reason that the Schrödinger equation is a deterministic equation. It's a linear equation. So it would imply that we observe microscopic superpositions, but we do not. And then the three options basically to the measurement problem are either to say, no, the wave function does not describe everything. So there is something beyond the wave function. Then the second option is to say, no, the Schrödinger equation is not correct. Or at least to say that, that the wave function does not always behave according to the Schrödinger equation. And then there's also a third option that has become more popular recently and that was not taken into account by Bell, namely that we do, as a matter of fact, observe microscopic superpositions in some sense, that we live according to the many worlds interpretation. So the many worlds interpretation would say that whenever a quantum event takes place, reality branches or splits up in every possible measurement outcome. So yeah, when I observe spin up, so when the wave function describes it as a superposition of spin up, spin down, then I do the measurement and I observe spin up. Then in a different branch of reality, I observed spin down. Okay, and the approach of normal, typical textbook quantum mechanics would be to say that the Schrödinger equation does not always describe the wave function, because when a measurement appears, right, when a measurement takes place, then the Schrödinger formalism is replaced by this collapse postulate, right? So the wave function collapses upon measurement. And for many philosophers, this is very vague, right? They would say, okay, what does it mean that a measurement is performed? Why does measurement play this role? So very roughly speaking, this is the context of the measurement problem.
And this mini-world interpretation, what issues does it have, sort of? Because intuitively speaking, it seems like, okay, you don't need to add anything extra, so why not go for that?
It doesn't explain anything. It doesn't tell you why anything like this happens. There is no description of why this should split. There is also no description of how you store the universes. I mean, it's not like you have once in a while a branching. Most measurements have continuously infinite number of outcomes happening in a universe which, to the best of our current knowledge, has an infinite spatial extension, or at least a very, very large extension, which means that you have like arbitrary infinite number of universes branching at every instance of time. What does this mean? How does this work? Where are these universes? What kind of reality structure you have? So that is something which is left out. You just say the universe exists. What does this mean? I mean, we don't even know what it means for a single universe in a classical theory, but it exists, because there's no explanation of where it comes from, what it is. From that point of view, it's not particularly attractive.
With respect to the many-worlds interpretation, I think it's really nice or interesting that many people really dislike it very much and some people really like it very much. Yeah. So when it was
There's
invented...
no in-betweenness.
There's no in-between. There is no in-between.
Yes. But it's much more popular with the philosophers than with the physicists.
Mm. So in philosophy, some very, very popular philosophers of physics, some of them have been in Oxford. One of them is David Wallace, who has been in Oxford, who is now in Pittsburgh. They're very outspoken about this, and they are very good philosophers of physics. And yes, the main selling point is precisely what you said before, namely that, so the main selling point is that they say, this is the most, mathematically speaking, like the simplest theory, right? You only have the Schrödinger formalism, you only have unitary quantum mechanics, and you don't need anything else, decoherence and so on. But it is quite simple, and for instance, Bohmian mechanics, and what is, I guess, one of the main selling points is that they do not need this notion of measurement, right? They say you have this objective description of reality. And there are also some famous physicists, for instance, Joe Carroll, a physicist, is also an outspoken proponent of the many-worlds interpretation. And he has this theory, what he called mad dog Everettianism, which really is the view that Hilbert space is fundamental space. It's like the lightest version that you can have of everything, right? When it comes to the formalism, you just have the Hilbert space. This evolves according to unitary quantum mechanics, and you don't need anything else. Many people find it, like I said, very, very implausible, right? That we live in Hilbert space, which is an abstract mathematical space, and that reality branches, and that we have infinitely many worlds and branches of reality. And also many people point out that it's not falsifiable, right? So typically, many philosophers of science really press the importance of the possibility of falsification, that you can falsify a theory or an interpretation. And with respect to the many-worlds interpretation, this does not seem to be the case. You cannot see the other universes, right?
But I mean, the main problem with this all is the measurement problem arises because by construction, the quantum mechanical axioms do not include the measurement apparatus. So the measurement axiom of quantum mechanics postulates that measurements are done from outside the system. As a consequence, you don't have a formalism which allows you to describe measurement itself. Now, you can, of course, start and say, okay, I try to push the measurement apparatus onto the quantum system, trying to model that. And if you do this, then at least you see that if you add simple-minded models, you get that expectation values become more and more classical-like.
What do you mean by this?
That means that classical behavior, as we see, is something which, as a quantum mechanical observable, becomes the typical case. So you lose more and more of the quantum system, of the quantum nature, the more complicated the system is you describe, mostly. And so if you try to model a simple experiment acting on a quantum system inside a wave or combined wave function, you see that it easily gets that the wave function gets more and more like, okay, it's something which is concentrated at a single point, meaning it behaves more and more particle-like. So the question is always, okay, can we get rid of the idea of having the whole measurement process? Can we get rid of the measurement postulate and just describe everything in terms of the quantum system? The thing which you usually end up with, okay, why do I perceive classical physics? And then you end at the boundary that if you push the system more and more towards your own mind, you end up with the problem again, what is mind? Okay, that is something which is, I think, a possibility which many physicists entertain, saying, okay, it is just because we don't measure it. I mean, it's also extremely interesting to see if you unify relativity with that, then in quantum field theory, there is no possibility for the notion of an outside, because all of space-time is required to write quantum field theory down. So there is no point where you can...
There's no system, no environment in a sense.
Yes,
There's
no environment in the description of the theory. And as such, it becomes very hard to even formulate the measurement process. So the only thing which you have are expectation values. And that's basically it. So it's a question of whether our description of the measurement process at the moment is really adequate. And there are many people who have developed possibilities like quantum probability theory, which are more pushing to the idea that the measurement problem is, or the measurement description is an artifact of an incomplete description of the mathematical apparatus.
So do you think that a theory, like both from the philosophical and physical point of view, should have encoded some axioms or some way of introducing the measurement problem always? Because otherwise we end up with this maybe inconsistencies. Because before you said quantum mechanics doesn't have any axioms about how the measurement works. So is this really incompatible with quantum mechanics as a just...
No, that is something which needs to be empirically found. It appears attractive to many physicists to say, okay, the measurement problem is an artifact of an incomplete description. Many physicists would certainly be willing to accept that things like the wave function are real, and that classical physics is basically a coarse graining of wave function probabilities, that essentially a classical physics is an illusion. Really, you live as a wave function, and our mind is, due to evolutionary necessities, trained to ignore the fact that it's not perfect, because there is this coarse graining involved. And that is certainly an approach which is consistent with what we see, though we are lacking a full mathematical formulation to test it.
Yeah. So this view that the wave function is real, it's called wave function realism, unsurprisingly. And
with a lot of fantasy.
And I mean, one of the questions is then, okay, when you say that the wave function is real, what about the space in which it is defined, right? Is Hilbert space also real? Many philosophers of physics think about this in terms of something like a configuration space realism, that configuration space is real in which the wave function lives. And I think many philosophers of physics, like I said, are really annoyed to some extent about the notion of measurement, and they feel like we should have a purely objective view on the world, and that quantum mechanics needs to be modified, at least textbook quantum mechanics needs to be modified in the way, for instance, of Bowman mechanics or objective collapse theories, such that the notion of measurement disappears. And it also seems to disappear in the many worlds interpretation. But perhaps you could also go in the opposite direction, right? You could also think maybe at the fundamental level, something like a completely objective description of reality is not possible, and maybe the fact that the term of measurement pops up in quantum mechanics is not a bug but a feature, right? But these are open questions. Yeah.
Is there a particular interpretation that you consider most convincing?
Personally.
No, I don't think that one is most convincing, but I think that some interpretations deserve more attention, in particular by philosophers. And so it seems to me, I've made the experience that more philosophers are working on objective interpretations, like Bowman mechanics, which is a bit strange, right? Because then you have to modify the formalism, but philosophers are not best equipped to modify the formalism because this is a technical stuff. And then you need to make it consistent with special relativity, which is also very technical and difficult. So this is more something like a problem for physicists, I think. And I have some interest for more subjective interpretations, like, for instance, cubism. Cubism would say, no, the wave function is not real. It would say no, quantum probabilities are not objective probabilities. the wave function, the quantum state, it only represents subjective degrees of belief. Quantum probabilities are subjective in a Bayesian sense. So Bayesian is an approach to probabilities in general. So this would be a subjective interpretation of probabilities, a subjective interpretation of quantum probabilities. And then the question is how to make sense of this, right? How to make sense of this, that now our fundamental physical theories, or at least one of them, quantum mechanics, is not about objectively describing reality, but is more about how do we experience the world, and based on this, what predictions can we make?
What do you mean with subjectively? How can it be subjective?
It's subjective in the sense that the wave function is not something objectively existing. Subjective in the sense that probabilities are not interpreted as objective probabilities, but as subjective probabilities that somehow encode degrees of belief of the respective agent. But it is not anti-realist in the sense that it would neglect or say that there is no external reality. It would just, so to speak, just be anti-realist regarding the wave function. So the wave function is not physically real, and the formalism does not provide us with a formalism about how reality evolves in time, but it tells us, given a particular experiential input that can be encoded in the wave function, we then can predict what is most likely for us to expect to experience next.
So as it turns out, today's episode was very, very long, but also very fascinating. That's why we have a follow-up coming in 2 weeks, so stay tuned. And by the way,
if you want to contact us, just send a mail to bridgethegap@tugraz.at.